Hello, and welcome back to the Validity Podcast. I'm your host, Valentina Rodriguez, and this is episode 5 of season 2. We are well into my fall semester of my second and last year at USF. I will be graduating in December, and we are in the thick of the semester. I'm literally in the middle of midterms. You guys know that most of the content from these episodes is coming from my neuromuscular exercise physiology class, and I have a midterm on that on Thursday. So in 2 days, because I'm recording this on a Tuesday, and then the following Monday, I have a stats exam, and then my mom is flying in the day after my stats exam. There is a rapid fat loss study being done in person as part of our lab. I'm not leading that one. I am leading the world's first reverse dieting study. That is a virtual study. So if you want to join the reverse dieting study, just email reversedietstudy@gmail.com. But the rapid fat loss study is a very small in-person study led by one of my colleagues and other coordinator, Landon, and my mom's going to be a subject in that study. It's basically looking at this really extreme rapid fat loss kind of protocol that we actually discussed in the rapid fat loss strategies episode way back in the early days of this podcast. So if you're interested in what that protocol looks like, it was the 4-day extreme rapid fat loss protocol done on obese men. So this study is essentially replicating it in women that are in different stages of their menopausal status, if that's kind of their menopausal status. So my mom is going to be here for a week to undergo that study. So just lots of busy things going on. So in terms of today's episode is going to be part 1 of discussing muscle damage, what is occurring physiologically at the muscle fiber and muscle cell level, but also discussing some protective mechanisms against muscle damage. And so we're splitting this up into 2 parts. I'm going to record both episodes today because I have no clue what my next week is going to look like, but hopefully they will build upon each other and give you guys just a better picture as to what we talk about when we talk about muscle damage, what's happening at the cellular level, and different practices that you can implement that will tie into the episode that I did on preventing injuries. So if you're an avid listener, you're gonna see a lot of dots connect between last season's episodes and this season's episodes, and it's gonna start to build a really nice picture, hopefully. So when it comes to personal updates, I don't have much. Still recruiting for the reverse dieting study. As you guys know, recruitment email is below. I am almost 10 weeks post-show, still hovering around 5 to 6 pounds above stage weight. So definitely starting to trend upwards, definitely feeling a little softer. But I will say, I just got back from the wedding last weekend. And in the past 12 days, I've taken 5 days of full intuitive eating and 2 free meals. So I've only been on my exact protocol. Obviously, all that flexibility was approved by my coach, Shelby, but in the past 12 days, I've only had 5 days of like perfectly adhering to my protocol. And one of those days I woke up super late and I ended up being short a meal. And I don't consider that perfect execution. You guys know I'm kind of a little bit anal, so to say, about the way I execute. So in the past 12 days, I've really only had 4 days of perfect execution on my macros, on my meals. And that is not okay with me. So I have a pretty long stretch without free meals coming up, just because I need that. But I am really fucking happy, honestly, that I was able to take as much flexibility as I did. Enjoy the wedding. Was such a great weekend. Just have quality time with my boyfriend and with friends. And I'm pretty much still within a pound of, like, even today, 12 days later, I'm still less than a pound up from the day that I left 12 days ago for the wedding and for all the shenanigans and whatnot. So yeah, I'm just honestly just excited to get back on my meals. I'm doing a full day of eating on my reverse diet on my YouTube. That's the next video that's out. The first video is already out with judges' feedback and post-show updates. So other than that, and just being in the thick of midterms and PhD applications, we're going to get straight into the science because I have such a busy day today. I cannot just keep yapping about things that you are honestly not here for. You are here to learn about muscle damage. So we have different mechanisms of muscle damage, but the biggest thing that you need to know is that the most damaging type of contraction is an eccentric contraction. So whenever you are lengthening your muscle in the active state, so not just lengthening your muscle, but you need to be contracting and lengthening. So think about a bicep curl, it's when you're lowering the weight. Think about a hamstring curl, it's when you're lowering the weight. If you're thinking about a tricep extension, it would be when you're actually bending your arm, not extending it, because it's all relative to the muscle that you're talking about. So the most damage that is done to the muscle cells and muscle fibers, and we're going to talk about different places where that damage occurs, is going to be done specifically lengthening contractions, which are eccentric contractions. And so the theory is that lengthening contractions or eccentric contractions causes mechanical stress, and they activate stretch-activated channels or TRP channels. That mechanical stress can damage the excitation contracting coupling mechanism, which is the neuronal pathway of whenever it goes from brain signal, activate the contraction. It may damage cytosolic proteins, your extracellular matrix proteins. It may damage your cell membrane. And those stretch-activated channels in response to these lengthening contractions that are activated can go on and actually increase the opening of calcium channels, which increases calcium influx into the cell, activates proteases, and that further causes damage to different parts of the muscle cell. So we're going to go through all of that today. And then in the next episode, we're going to talk about a protective mechanism against muscle damage. So let's talk about mechanical stress, because that's one of the first things that's kind of induced by these lengthening contractions. And so, as I said, lengthening contractions produce the greatest amount of muscle damage. If you do an isometric contraction in an elbow flexion at 90 degrees, you get minimal damage. But the more that you extend it, when you get to 20 degrees, you start to induce muscle damage. And it appears that it's from mechanical damage to muscle fibers when you're contracting at these longer lengths. If you remember the episode where we talked about titin and we talked about lengthened partials, we talked about how titin is a molecular spring that's activated whenever you are contracting and lengthening your muscle. So it's activated in the eccentric portion of the movement. And titin is a molecular spring. It's a structural protein that may have a role in anabolic signaling if lengthened partials are indeed more hypertrophic, which we don't know for sure if they are. It could be due to titin's role. It could be due to maybe more damage done at the lengthened portion of the contraction. We don't know. We don't know if it's more hypertrophic, but I want you guys to start connecting the dots if you did listen to the episode on titin and on lengthened partials. So I would go back and listen to that and maybe try to draw some connections for yourself. But essentially, there's different factors that contribute to exercise-induced muscle damage, or EIMD. That would be the number of contractions. So more lengthened contractions, more muscle damage. The force, and it's actually the amount of muscle fiber strain and not the absolute amount of force that's related to more muscle damage. And then your lengthened contraction velocity. So faster lengthened contraction, more muscle damage. One of the kind of factors that we think about when we think about muscle damage is soreness. And a lot of times we think, if you're really sore, you probably induced a lot of damage. And a lot of times the narrative is like, oh, you damage your muscle and you repair it, and then that's how you grow. That's how you see hypertrophy. And a lot of people ask, oh, if I'm not sore, did I train hard enough? Like, am I doing something wrong if I'm not getting sore? Let's kind of dispel all those myths right now. So Jones and Round in 1990 found that DOMS, or delayed onset of muscle soreness, could actually be indicative of inflammation of your connective tissue. And this would support the relationship that we see between soreness, creatine kinase activity, and decreased muscle function. I'm going to pause really quickly and bring up creatine kinase, because I know a lot of times if you go get blood work, you might get a reading back in your biomarkers of your creatine kinase or of your creatinine or whatever, and it might be upregulated, and you might think, oh my God, am I eating too much protein and now I'm having like elevated blood markers of creatine or creatine kinase or whatever. No. A lot of times if you see elevated levels of CK in your blood work, you'll get asked, did you train before your blood work, like the day before or even up to 2 days before, or especially so the day of? You should never train before your blood work. That's because creatine kinase is a cytosolic protein, meaning it lives in the cytosol of your muscle cell, that whenever you have muscle damage can easily permeate out of the cell and actually seep into your serum. Serum is your blood plasma. And that's why you see elevated levels of CK in your blood work after training. So there is a relationship between soreness, your creatine kinase activity, and decreased muscle function. But Jones and Round also speculate that it could be afferent signaling from spindles. I'm not going to get into that, but it's just basically saying DOMS might be muscle damage, it might be connective tissue damage, it might not be. We don't really know, but if it is connective tissue damage, it would support the relationships that we're seeing between soreness, creatine kinase activity, and decreased muscle function. DOMS et al. In 2018 looked at skeletal muscle hypertrophy through resistance training and the role of muscle damage and muscle protein synthesis. And they actually speculated that the initial increase in muscle protein synthesis that you see right after your initial bout of resistance training is actually due to the damage repair and is not correlated with the consequent hypertrophy that you see after chronic resistance training. So it's essentially saying that this initial upregulation of your muscle protein synthesis only is going to contribute to hypertrophy when your muscle damage is attenuated or minimal. Meaning, if you get this upregulated level of muscle protein synthesis after the initiation of resistance training, and it's mostly upregulated to repair damage, that upregulation is being allocated to damage repair, therefore it's not going to contribute to hypertrophy. So if you minimize the damage, that upregulation of muscle protein synthesis can actually then contribute to hypertrophy. It's almost like saying you upregulate your muscle protein synthesis after training, but if you damage your fiber too much, you're going to be taking away some of that muscle protein synthesis from hypertrophy and actually allocating it to damage repair, and therefore that MPS upregulation is not contributing to hypertrophy. Does that make sense? So this specific group of researchers, DOMS et al., are speculating that damage would actually work against your muscle protein synthesis, contributing to hypertrophy and growth. And essentially they say that resistance training with less damage would still produce similar hypertrophy and strength outcomes, and that damage does not mediate or potentiate resistance training induced hypertrophy. So food for thought, I guess, for those who think that you need to induce damage or need to be sore or this or that after a training to see growth. DOMS et al. Would be like, actually, you don't. So another study by DOMS et al. Looked at early resistance training increases in cross-sectional area. They did a 10-week training program. They took measurements before, 3 weeks in, and then at the end of the 10 weeks. And they found that from pre to week 3, there was an increase in cross-sectional area that then decreased between weeks 3 and weeks 10, suggesting that the increase in the first 3 weeks of cross-sectional area was due to muscle swelling or edema. So your muscle cells filling up with water as an inflammatory or swelling response to the initiation of training, essentially. And that it's hard to determine if growth is occurring within the first 3 weeks because you cannot separate those changes seen. You can't determine which of those were real growth, real changes in cross-sectional area, and which were due to edema or swelling. The last study that we looked at in regards to muscle soreness and swelling and all of that is by Leinecke et al., published in 2014, and it was looking at, does blood flow restriction cause damage? And they concluded that there's little to no damage caused to the muscle fibers by blood flow restriction, but you still see growth outcomes. And they determined that there was little to no damage because they found no prolonged decreases in muscle function, no prolonged swelling. Soreness ratings in the blood flow restriction group were similar to the control group, which was a sub-maximal low-load control. So doing really lightweight, not to failure without BFR, so something that you would not expect to see damage in. And the soreness ratings were similar between the two. And there were also no increase in muscle damage biomarkers, so no increases in CK levels, etc. So this study kind of suggests that, at least with blood flow restriction, you can see growth without inducing significant, if any, muscle damage. So for those thinking that you need to tear down and genuinely damage your muscle, you don't, not according to a lot of these researchers. So let's talk about what that muscle damage actually is, because I think a lot of times we talk about muscle damage as this like umbrella term, and now we're actually going to look at what that damage looks like. So we can see damage to the filament. So filament damage, essentially, lengthened contractions produce greater force than shortening contractions while recruiting less motor units. This is going to tie into something that we're going to talk about in the next episode in part 2. But what you need to know is that you are stronger in the eccentric than you are in the concentric. So if I give you a barbell and I tell you to curl it up, the amount that you can curl up is going to be less weight than if I give you a barbell. You're starting at the top position with your hands by your shoulders, so like the top of the bicep curl. If I put the weight on you at the top and I ask you to lower it slowly, you're going to be stronger lowering the barbell than you are raising the barbell. You are stronger in the eccentric. You are stronger in a lengthening contraction than you are in a shortening contraction. Okay? You're stronger in the eccentric than you are in the concentric. And another interesting thing is that you actually recruit less motor units in the eccentric than you do in the concentric. So you recruit less motor units when you lower the weight than when you raise it. And this is important because if you can lift more weight while lowering it, but you're recruiting less muscle fibers, that means that each muscle fiber is taking on more tension in the eccentric, which gives more opportunity for injury. And there's greater levels of tension in this stretched sarcomere, and that can disrupt the overlap between myofilaments, so between actin and myosin. And therefore, your cytoskeletal protein matrix, so what's kind of holding everything together in simplistic terms, also bears greater tension in the eccentric. And all of these things can actually damage your filaments. It can damage your actin. It can damage your myosin. Another thing that can get damaged is your intermediate filaments. And these are proteins that exist between your actin and your myosin to kind of hold everything together. One of those is titin. Another one is something called desmin. So muscle injuries from eccentric contractions involve disruptions to your intermediate filaments, and these intermediate filaments normally contribute to passive stiffness and to the structural integrity of your sarcomere architecture. So damaging those kind of puts the entire sarcomere and the entire muscle cell essentially at risk. And desmin is the most prevalent intermediate filament protein in your skeletal muscle cells, and they link the Z disc to each other and link the Z discs to the cell membrane at the myotendinous junction. So all you need to know is you have sarcomeres, which are like orderly arrangements of actin and myosin. That's kind of what makes up your muscle fiber and what gives it the striated appearance. And the way that you hold those together and you actually keep those in place is by desmin holding them to each other, but then desmin also adhering those to the cell membrane so that they're not just floating around your cytosol, right? Like they need to be anchored, and desmin anchors those to the cell membrane. And it was found that after eccentric contraction, you start to see these desmin-free zones. So zones in your sarcomeres that are devoid of desmin, which suggests that there are some selective proteases, and proteases are enzymes that degrade proteins. Basically, a protease is anything that's going to break down a protein. So it suggests that there's this activation of proteases that are selective for desmin that are basically breaking down the desmin in these zones, and that is putting at risk the structural integrity of your sarcomere. And we see this upregulated. We see these desmin-free zones upregulated after eccentric contractions. So it's an important kind of phenomenon that we're seeing. We're seeing there's definitely like a compromise to your sarcomere integrity via desmin that occurs after eccentric contractions. And the mechanical stress of an eccentric contraction also disrupts your excitation-contraction coupling. That means the pathway that goes from your brain sending the signal all the way down to your alpha motor neurons that are essentially going to communicate to your muscle cells like move, contract, this, that. That entire pathway of signaling from brain to muscle can be damaged by eccentric contractions, by the mechanical stress induced by eccentric contractions, and that decreases your overall force production. And specifically, this disruption occurs at the connection between your T tubules and your ryanodine receptor. And this requires a lot of background info that I don't think we need to get into, so I'm going to simplify it super fucking easily, hopefully. Is you have an action potential, which is an electrical signal from your brain. That's how your brain communicates, is action potentials. That action potential causes the release of a neurotransmitter called acetylcholine. That's what binds to your muscle cells and eventually transmits that signal from nerve to muscle and says, hey, contract. That signal, when acetylcholine binds its receptor, it creates another potential called the end plate potential. That end plate potential needs to travel down these structures called T tubules. Those T tubules will then activate L-type calcium channels that release calcium. Calcium binds to a receptor called the ryanodine receptor, which releases more calcium into the cell. And then that calcium can then bind troponin, move tropomyosin, actin binds myosin, and then you get a contraction. So that was really complicated. I said I would simplify it. I realized I did not. But what you need to know is that the connection between T tubules and ryanodine is important because it's what allows adequate calcium signaling to start the contraction. And what connects T tubules to ryanodine is called junctophyllin. And we see decreased levels of junctophyllin following 50 lengthened contractions. And that causes a decrease in your force. So there is a disruption of the signaling between T tubules and ryanodine receptors that is documented via this decrease in junctophyllin levels. And this is another kind of consequence or a different place in which muscle damage can occur. So we've seen muscle damage at the filament level just via the fact that we can lift more, but lift more with less muscle fibers, meaning muscle fibers take on more load and more tension in a lengthened contraction versus a shortened one, which can damage your filaments. We see intermediate filament damage, especially in desmin, because we see these desmin-free zones that put at risk the structural integrity of your sarcomeres. And we also see this disruption in the signaling from brain to muscle via the decrease in junctophyllin, which connects your T tubules to your ryanodine receptor. So that's kind of 3 places so far where we see where damage can occur in response to eccentric contractions. Another place, and possibly the most kind of consequential, in my opinion, place where we can see damage is at the cell membrane. So the cell membrane also gets damaged during injury or during eccentric contractions. And what you can see, sometimes visibly see on a microscope, are these cell membrane lesions, which are these essentially holes in your cell membrane. And the problem with these holes is that they disrupted the regulation of proteins going in and out of the cell. Okay. So you start to see this unregulated influx of extracellular markers, things that should not be in the cell, start to come in. And you start to see this efflux of cytoskeletal proteins, one of those being creatine kinase. And that goes back to why you see elevated levels of creatine kinase in your blood work after you train. If you train the day before you got your blood work done, it's because that's one of the proteins that are kind of going unregulated and spilling out of the cell when you have these cell membrane lesions in response to eccentric contractions. And we see that this increased accumulation of extracellular markers in the cell and of intracellular proteins out of the cell, we see that can be progressive for days. It doesn't happen immediately. And so this delay indicates that damages to the cell membrane might be caused by factors that are secondary to mechanical damage. And we will discuss those in part 2. So another issue with this unregulation of flux of proteins coming in and out that are not supposed to is that it allows for the rapid diffusion of small ions to follow concentration gradients that should not be occurring. So you actually get this rapid and immediate influx of calcium into the cell. And calcium is a critical signaling molecule. It's a critical signaling ion. It's so critical in so many different pathways, and it's normally very highly regulated. You normally have a concentration of 1.8 millimoles outside of the cell. And when you get these lesions and these proteins start to come in and out, calcium starts to flood in. And the problem with calcium flooding in is that it can activate calcium-dependent proteases. We talked about how proteases are enzymes that degrade proteins. We talked about how those were potentially selectively degrading desmin and therefore compromising the integrity of the sarcomere. Well, these calcium-dependent proteases are called calpains. And calpains seem to be activated in response to injury. I wonder why. Could it be because there's cell membrane lesions that are allowing the dysregulation of protein fluxes that then causes calcium to flood into the cell and activate calpains? Maybe, but this has not been proven. However, it is highly suggested. So these increases in calcium concentrations in the cell cytosol, so in the cellular matrix inside the cell, increase calpain activation. And we see these last for over an hour post-eccentric contractions. And when this calcium concentration increases and calpain activity increases, it's normally regulated by calpistatin, which is an inhibitor of calpains. But if there's too much calpain per calpistatin, you're still going to see that activation predominate. And we see that desmin and another intermediate filament protein called alpha-actinin, those can be injured with eccentric contractions, and it could be a result of these calpains selectively targeting these structural proteins like desmin. And Belcastro et al. Actually proved that and found that calpain activation was linked to desmin or alpha-actinin degradation caused by changes in calcium concentration. So we do have the evidence for that. Similarly, Giselle et al. Were looking at calcium influx and skeletal muscle damage. They essentially electrically stimulated muscle cells to stimulate an eccentric contraction. And they found that increased cytosolic calcium concentrations. And that caused an increase of calpain and phospholipase activation, which we'll talk about in a second. And that decreased sarcolemma, which is your muscle cell membrane integrity. So let's talk about that. Let me break that down again. Electrical stimulation to a muscle cell, mimicking an eccentric contraction, they saw increases in cytosolic calcium, which then saw increases in calpain and phospholipase activation, which then saw decreases in sarcolemma integrity. And this continued for up to 120 minutes or 2 hours post-stimulation. So this was another kind of piece of evidence connecting eccentric contractions to changes in cytosolic calcium concentrations to calpain activation to compromising your cell membrane and your sarcomere integrity. I just said that they saw increases in calpain and in phospholipase activation. So now let's talk about phospholipase activation. Phospholipases are just part of your cell membrane. You have a lot of phospholipids that make up your cell membrane. So these are lipid or fat molecules that have like these phosphate groups or phosphate heads. And phospholipases are enzymes that break down phospholipids. So lipase will always mean break down fat. Phospholipases break down phospholipids. And phospholipases they're expressed constitutively in skeletal muscle cells at the skeletal muscle cell membrane. However, they're typically inhibited, so to say. And specifically, when you get this increase in cytosolic calcium concentrations, you also see this activation of phospholipase A2. We also call it PLA2. So PLA2, again, is constitutively expressed at skeletal muscle cell membranes. And what their role is, they hydrolyze glycerol, which is a part of your phospholipid structure. They hydrolyze glycerol into arachidonic acid. And so not only are they breaking down the phospholipid, but arachidonic acid, which is what they produce, is an inflammatory eicosanoid, meaning it's an inflammatory signaling molecule that's going to go on and promote inflammation, which is part of the response we see to skeletal muscle damage. So it's kind of like a cyclical thing. What came first, chicken or the egg? Kind of all of it keeps it all going. So we see that increases in PLA2 activity cause damage to myofibrils that resemble eccentric contraction damage. So if you simply increase PLA2 activity in a cell, you're going to see a similar outcome as if you had put that muscle cell through eccentric contractions. And another thing that these phospholipases might do is they might promote the production of free radicals, which are these really, really reactive species that you don't want in your cells because the lipids that make up your cell membrane are really reactive. And so it can kind of offset everything. They can damage a lot of structures. So you don't want free radicals. But we see that the production of these free radicals, specifically superoxide and nitric oxide, are low in resting muscle, but they increase tenfold at the onset of a contraction. And if you inhibit PLA2, you see a reduction in this free radical production. And this is specific to the calcium-dependent isoform of PLA2, which links not only PLA2 to free radical production, but it links this increase in cytosolic calcium to free radical production. So now we know that this increase in cytosolic calcium not only is going to activate your calpains and degrade proteins that you don't want degraded, but it's also going to activate your phospholipase A2 and degrade part of your cell membrane that you don't want degraded. And it's also going to cause free radical production, which can go on and have greater detriments to your cell membrane because it's made up of phospholipids that are highly reactive and especially highly reactive to free radicals. So that's kind of, again, this loop, the cyclical thing of what came first. The cell membrane was damaged, which allowed proteins to influx and efflux in an unregulated manner, which allowed calcium to flow in, which allowed calpain and phospholipase to be activated, which allowed the membrane to be damaged. But the membrane damaged is what allowed the calcium to flood into the cell. You see where I'm going? It is the cyclical thing of we don't know what came first, what came second, what came last, what came in the middle. But we do know that we see all of this occur in response to eccentric contractions. The last thing we're going to talk about in this episode is inflammation. So there is a delay in the appearance of these cytosolic proteins in your blood after injury. So they don't happen immediately. They happen in the following days, okay? And it suggests that inflammation and this efflux of cytosolic proteins into your serum is not a direct consequence of mechanical stress, but rather of a different delayed injury mechanism. And we see this in a study that was done on rodents, and they basically took the hind limb muscles and they unloaded them, so they took off weight, and then they reloaded them and induced mild injury. And they found that cell membrane lesions did not occur at the onset of reloading, but rather increased over several days post-reloading. So it took several days after putting load back on and inducing injury for those cell membrane lesions to start to kind of pop up. And we speculate, or researchers speculate, that these cell membrane damages may be because of an increase in inflammatory proteins, which could be, we talked about arachidonic is an inflammatory signaling molecule. It promotes inflammation, and arachidonic acid is produced by phospholipase A2, which is activated by calcium. So again, what came first? I don't know. But I do know that It's happening. And the evidence that we have in humans to support that cell membrane damage is caused by inflammatory proteins is that muscle damage signs post-eccentric contractions coincide with increased neutrophils in the cells. Neutrophils typically are in charge of coming in and getting rid of debris and getting rid of trash, basically, that you don't want in the cell. In rodents, the evidence that we have for this is, again, this unloading, reloading study done to the hind leg of these rodents showed an increase in neutrophil invasion. And that suggests that neutrophils may promote damage to the cell membrane outside of their previously thought primary function of removing debris. And we do have some data that suggests that if you block neutrophils, you decrease post-eccentric contraction muscle damage. So block neutrophils, do eccentric contractions, you see less damage than if you hadn't blocked the neutrophils. So neutrophils are also playing a role in further damaging the cell membrane. And that is where I'm going to leave you guys for this episode. I just kind of wanted to go through the different pathways, places, sites where we might be seeing muscle damage in response to eccentric contractions. I wanted to leave you guys with some food for thought as to how can we reduce the damages that we're seeing? How can we reduce calpain activation, phospholipase A2 activation, neutrophil invasion, cell membrane lesion, intermediate filament damage? How can we reduce that? We're going to talk about that in the next episode. But in this episode, I just kind of wanted to go through the different places where we see muscle damage, because I know we talk about it usually pretty fucking vaguely. And from there, we're going to talk about protective mechanisms to muscle damage. But the biggest things I want you guys to take away is now you know what we mean when we say muscle damage. You might be thinking like a bicep with tiny, tiny little tears in it. You would technically not be wrong, but really it's like structural degradation of sarcomeres, of cell membranes, invasion or compartmentation of certain proteins and ions that should not be in the places that they are, et cetera, et cetera. And also, as we talked in the beginning of the episode, you now have evidence that damage is not necessary for growth. Soreness is not indicative of damage, and soreness is not indicative of exercise efficacy. In fact, next episode, we're going to talk about how soreness is not even the best marker for muscle damage. So yeah, that's it for this episode. I hope you guys enjoyed. I know it was a lot of science. I think this season in general is a lot more technical than my past seasons, and I hope you guys are enjoying that. Please give me feedback, because I can always deviate from what we're covering in class. I do want this podcast to be like a direct representation, a direct liaison between my master's education and you guys. But if you guys would rather I deviate from what I'm learning because it's just too technical, I can always go out and seek out more relevant literature that we can go through together. That's what I will do when I finish my program and I no longer have classes to take content from. So I figured I would do this until I'm done and have no other option and enter my PhD, which would probably be more technical than even this. So just give me that feedback. But until then, you guys already know, if you have any questions, you can email me at my personal VallFitt_IPB Pro, at my podcast Instagram. First episode of Pro Off-Season series on YouTube is out now. Full Day of Eating is coming soon. Reverse dieting study is still recruiting, so you can email the email below. And I will see you in the next one.